Welcome to chapter 15. We'll be talking about equilibrium of other reactions. Really, it just means dissolving things. So we'll start looking at defining what's called the solubility product, a special type of equilibrium constant, KSP. So we want to look at the idea of solubility. We defined this back in chapter 11, at the start of class, about the idea of soluble compounds that dissolve and insoluble compounds that don't, right? You have water, some things dissolve in water, some salts dissolve in water, polar molecules tend to dissolve in water, and non-polar molecules don't, right? So this idea of this kind of binary option, soluble, insoluble, what is kind of the reality, and you have this kind of pairing of possibilities of, for any solute-solvent pair. And so we would say silver chloride is insoluble in water and sodium chloride is soluble in water. So we can write what would happen if they dissolved in water. Since they're ionic salts or ionic compounds, they would separate into their distinct ions, and they'd be floating around. So we say this doesn't happen, right? Silver chloride doesn't dissolve in water because it's not soluble, whereas the sodium chloride does dissolve. We start with solid sodium chloride, and then it dissolves into its separate ions, right? They're all together in the salt, and then they start to be separated, floating around, and then there's no solid left, right? There's no solid left when we put it in there. But really, dissolving of silver chloride in water is in equilibrium. So you put your chunk of, say, solid silver chloride, where is it? You put your chunk of solid silver chloride into water, and most of it stays in the solid. But there are ions that dissolve into solution. Some, not many, and most of it stays solid, but some always is out there. And this is actually true for all dissolution. Anytime you're looking at any possible dissolving, basically it's going to happen to some extent. Now, it's not small. So oil and water, for example, don't mix, right? We get those layers. Oil is very nonpolar, water is very polar, so they don't intermingle. But some molecules do move. Yes, in general, you have your liquid phase or water phase and your oil phase that are mostly those things, but a small amount of water goes into the oil, and a small amount of oil goes into the water. It is a very small percentage of the molecules, but importantly, it's some. So whenever there is a possibility for a process to occur, whether or not it's a chemical reaction or a physical process like dissolving, if there's a potential for it to occur, a little bit will happen. If you can write it down, a little bit will happen. That's the point of equilibrium. But very low concentration. So, practically, if you wanted to do this, there's not really much mixing at all, right? It stays very kind of these two layers, water and oil. It's very, very small amount. It still looks like two different phases. So we define this idea of dissolving, especially for ionic compounds, and quantifying it using an equilibrium constant called the solubility product, KSP. So solubility product comes from the fact that when you dissolve in an ionic compound, we know it dissolves into separate ions. So as a result, the format of KSP, the form of the equilibrium constant, is always going to be a product of the ions, the ion concentrations. Right? So you have solubility product. So these solubility products are equilibrium constants, so we can characterize them as we've characterized other equilibrium constants. If KSP is greater than 1, that's a product-favored equilibrium, which means you get more product, right? So that's where we have a soluble compound. So for NaCl, sodium chloride, KSP, the value is going to always be greater than 1. So we're going to get dissolved ions. We're going to get that product in solution. Whereas when it's less than 1, it's reactant favored. That's an insoluble compound. So we can always kind of understand this. Now, KSP can be defined for any salt, and then it has a particular value to figure out whether or not the salt is soluble or insoluble. So let's get some practice. Write the expressions for the solubility product of the following salts. It's calcium sulfide, sodium sulfate, and aluminum sulfide.
Okay, so we want the expression for the solubility product for each salt. So when we see that solubility product, that is KSP. So this is solubility product, is the SP. This is just a particular type of equilibrium constant. And so basically, we just want the equation for the equilibrium constant. And our question should be, well, we know how to get equilibrium constants from chemical equations. So solubility product always means dissolving. So it's basically just, how does this salt dissolve in water? So I have calcium sulfide. I know that calcium sulfide, it will dissolve into calcium and sulfide, right? We know we just separate the ions. And so that tells me then that KSP is going to be products divided by reactants, right? But the reactant is a solid, so that doesn't show up in the equilibrium constant expression. I get Ca2 plus and S2 minus. And so we can really see here where the name solubility product comes from. This describes how many ions dissolve, right? These are concentrations of ions, i.e. dissolvedness, and they're literally multiplied together. That's where the word product comes from. So solubility product, they're generally going to always look like this because you're dissolving a salt, so the reactant's never going to show up because it's always just a solid. It doesn't show up in the denominator. You just basically multiply concentrations of ions. So if we then look at sodium sulfate, we know the sodiums are going to separate out from the sulfate. And we just want to be mindful that when we dissolve those, that we maintain our stoichiometry. So it doesn't just become like Na plus SO4 2 minus, because there's that 2 there. This isn't balanced, so there would be a 2 in front of the sodium. Right? You have here, there are 2 sodium cations per formula unit. So when it dissolves, those 2 sodium cations become independent of each other. KSP is still just going to be the concentrations of the products, but you'll note that coefficient becomes an exponent. So the concentration of sodium is squared times the concentration of sulfate. So still multiplied together, you do just have those exponents coming in. Aluminum sulfide is then dissolves into 2 aluminum 3 plus 3 of the sulfides. So the KSP is going to be the concentration of aluminum squared times the concentration of sulfide to the 3rd power. So whatever those coefficients in the dissolved equation, and the solubility equation, when the ions are dissolved, those just become exponents in the solubility product. You'll note they're always multiplied together. That's where the word solubility product.
Participation 1024, question 1. Write the expression for the solubility product of MgCl2. Is the first question on participation 1024, due Friday, October 24th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, write the expression for the solubility product of magnesium chloride. You know, when writing expressions, if you're typing them in the Blackboard editor, just kind of get them in the best order you can. Don't worry too much about formatting. When you're handwriting, you worry about formatting. Okay, one video down. We already have a question for participation 1024. That's due Friday. Week 9 homework's going to be due Saturday. Because this is the only set of videos, it's a smaller assignment, but still worth the same 10 points. We don't have any normal lab this week because of the test, but your lab group evaluation is due October 26th. So it's going to work like the first evaluation you did, but now it's for the second lab group. We're going to rotate again next week. So again, you're in the new groups. Take a look at the notebook, see what your role is for the upcoming week. If you have any questions about anything, let me know. Otherwise, welcome to week 9, chapter 15. See you in the next video.